Okay, welcome to part two of looking at applications of quadratic functions. So in this question, it's talking about a movie theater. So a movie theater can accommodate a maximum of 400 people in a day. That's how many they can bring in. The theater operators want to change admission prices from the current $5. They surveyed their customer and found out that for every 50-cent price increase, they're going to lose 25 customers. So this is really important. Every time they increase the price by 50 cents, they're going to lose 25 customers. They're going to be like, nah, too expensive, not going. The question's asking, what is the ticket price that will maximize their revenue, and what is the maximum revenue the company could potentially make? So we want to know the ticket price and we want to know how much money they could potentially make. What we're going to start off by doing is creating a couple of functions. So our first thing to note is that we need to discuss what our change is. So in this case, we're going to notice that every time we increase the price by 50 cents, we're going to lose customers. So our independent variable is how many times we increase the price. And we're going to let x represent that. So let x represent the number of 50-cent or $0.05 price increases. So we need to make our equation. Revenue is equal to the cost of the ticket, so how much the ticket's going to cost, times by how many people are coming. Now, if you look at our information that we got from this equation, we know that the current price is $5. So that's our initial value. That initial price is $5. And with every increase in price, it goes up by 50 cents. So our cost is equal to $5 plus 0.5, which is how much more money it's going to cost for each time we're raising the price. So that's where the x comes in. Each time we raise the price, the cost is going to be 50 cents more than the original. Now, the number of people is dependent on how many times we increase the price. So the maximum amount of people we can have in the movie theater is 400. And every time we increase the price, we're going to be taking away 25 people. So we're going to subtract 25 people for each price increase. That's where the x comes in. If you guys notice here, this looks very reminiscent of factored form. It's just a little bit, it's written a little bit differently. But this is a factored form of a quadratic equation. What this question is asking us to do is we want to know what the ticket price is when we maximize the revenue. Now remember, maximize. When we say maximum, that is a time where we want to go and find our vertex. In this case, if we go and find our zeros or our AOS, what it's going to tell us is how many price increases they're going to do. And then our optimum value is going to tell us how much money is the maximum amount they're going to bring in. So our first step is to find our zeros. And how we find our zeros doesn't change with this. We're going to make the bracket equal to 0, and then we're going to solve for x. So if we're looking at the first one, we're going to look at the cost bracket first. So 0 equals 5 plus 0.5x. We're going to shove 5 to the other side, it becomes negative, and we get 0.5x. Divide both sides by 0.5. And we're going to get x equaling to negative 10. Now we want to find out our other 0. So we're going to have 0 equals 400 minus 25x. To make things easier, we're going to bring this negative 4. So it gets negative 400 minus 25x. Divide both sides by negative 25. And our x on this side is equal to 16. So now we have our two zeros. When we go find our vertex, when we go from factored form to going and finding our vertex, we need to go find our AOS. So that's our step 2. We're going to find AOS. So our AOS is x plus our two zeros, so negative 10 plus 16 divided by 2. That's going to give us 6 divided by 2, which gives us 3. So our x at the AOS, so our x at our vertex is going to be 3. We can already find out now one part of the question. So that's what we're going to do. Our AOS is going to tell us what the ticket price will be at its maximum revenue. Remember, the cost of the ticket price is 5 plus 0.5, the number of increases in ticket price. There's 3 increases of our ticket price. So our cost equals 5 plus 0.5 times by 3, which is 1.50. That means $6.50 is going to be how much our optimized ticket price will be. We'll write a therefore statement for that later. Okay, so we found out our ticket price, but we don't know our maximum revenue amount. And how we're going to find that is by going and finding out our optimum value. And how we do that is by finding our R. And to do that, we're going to sub in our AOS into our equation. So we get 5 plus 0.5 bracket 3 times by 400 minus 25, again, bracket 0, 3. That's going to give us 6.5 times by 325, which gives us a maximum revenue of $2,000, $112.50. And this right here is our max revenue. So let's create our little therefore statement. Therefore, the max revenue is $2,112.50 at a ticket price of $6.50. So again, just to recap this question a bit, our revenue is equal to the cost times by the number of people. We find out our cost by noticing how many times it's going to be our current cost plus how many times the amount of the increase there is. Now, number of people is going to be equal to the maximum number of people minus how many people are going to say, nah, this isn't worth it, with each increase in price. Okay, moving on to the next question. This is a population question. We've kind of done one before, but let's go a little bit more in depth into this one. So the population of a city is modeled by the equation P equals 500t squared plus 10,000t plus 2,000, where P is representing the population and T is representing the time in years since 2000. So one quick thing to note, since it's saying since 2000, at 2000, so our year 2000, T equals 0. That's important. T equals 0, which means we're starting at that year. So our initial year is 2000. The first question is asking us, what is the population of 2000? That is our initial population. That is our y-intercept of our quadratic function. That is our C value. And our C value is 200,000. Therefore, the population in 2000 is 200,000 people. Now, again, reason why we can say it's our initial value is the year 2000 is when this graph starts. So at the year 2000, our t is 0. So we could just sub in 0 for t, and we would still cancel these out and get 2000. Next question is, what is the population in 2002? So since 2000, if we're looking at 2000 and we're going to 2002, there's been 2 years. So what we're going to do with this one is we're just going to simply sub 2 into the equation where t is. So we get 500 bracket 2 squared plus 10,000 times by 2 plus 200,000. That's going to give us a population of 222,000. Okay. Next question is, when is the population 350,000? So that means we're going to now put where P is a population. So in this case, what we're going to do is do 350,000 equals 500t squared plus 10,000t plus 200,000. What we want to start off by doing anytime we solve when we have something equal to a left side, we're going to move that over and make our left side equal to 0. So now we have 0 equals 500t squared plus 10,000t plus 200,000 minus 350,000. In our next line, that gives us 0 equals 500t squared plus 10,000t minus 150,000. What we're solving for is our zeros. In this case, we could go and do the quadratic formula, but these numbers are ridiculous. I have a sneaking suspicion that if we are to take out the greatest common factor, we might find that this is a very nicely factorable equation. Okay, let's try this out. There should be another 0 here. Let's take out that 500. What we're left with is t squared plus 20t minus 300. This looks doable. Looking at this, what we're going to be looking at is a product of 300 and a sum of 20. So negative 300 and a sum of 20. Okay. Our factors could be pretty straightforward. So our P is negative 300, our S is 20, and our factors are a nice positive 30 and negative 10. So that means 0 equals 500, bracket T plus 30, T minus 10. What we're going to do now is find our zeros. We're going to make each bracket equal to 0 to get T plus 30, negative 30 equals T. And on our other side, we have 0 equals T minus 10, so T equals plus 10. So if we have these as our two T's, these can correspond into years. So our first possibility of when the population was equal to 350,000 would have been 30 years before 2000. So 2000 minus 30 gives us 1970. Our other possibility is 10 years into the future, so 10 years after 2000, and that would give us 2010. So our two possibilities of when the population was 350,000 was 1970 and the other was 2010. This next example is asking us, we have a rectangular park. It measures 100 meters by 60 meters. A consistent width is to be paved around the perimeter because you know what, the mayors just really don't want us to have nice green areas for us to sit. No, we have to pave it over. The mayor of the city wants to be sure that the path does not reduce the area of the grass by more than 10%. What is the allowable width of the path rounded to the nearest 10th meter? So let's start kind of moving this into an equation that we see. So let's look at a little diagram. So this outer box in purple right now, what I'm going to label in purple, is the original width of the garden. So we have 100 meters by 60 meters. So this is our original area, which would be 100 times by 60, which would give us 600 meters, 6,000 meters squared. This is the original area that you would have had of green space. Looking here, the mayor wants to make sure that the path doesn't reduce it by 10%. So that means we need to see how much this width, if it's going to be constant. Yes, this diagram's not perfect, so it's not going to look perfectly constant, but from here to here and from here to here should be the same and same. Should be taking away the same amount with the path. Let's label this X for creative. So this width that's all around here is X. So if we're looking at this, our new area should take up 90% of the original area. Now, how did I get 90? They want to only take away a maximum of 10%. So what we would do is say if we're taking only away 10%, that leaves us with 90%. So if we want to find out how much our new area should equal to, can be no less than this, we're going to take 0.9, which is the decimal of the percent of 90, and we're going to multiply it by the original area, which is 6,000. That gives us a new area of 5,400 meters squared. So this is how much our new area should equal. So this lovely part in here, that's our area, that's our grass of 5,400 meters squared. All right. So if we're looking at this, we could start to label some of the information. The distance, the length right from here to here, is the 100 meters take away 2 of these x's, because this is going to be taken away. So we could relabel this as 100 minus 2x. Likewise, this section from here to here is this 60 meters taking away the x here and here. So it's going to be 60 minus 2x again. Let's see if I can write in here a little bit better. I'm just going to say 60 minus 2x. These two numbers here and here are our new dimensions. Something that we can always remember is that area is equal to length times width. We have our two new dimensions. It's 100 meters minus 2x for a new length. We put that in here. 100 minus 2x. The amount of path that's being taken away, or gravel. And our width is the 60 meters taking away the two lengths of the new pavement to get rid of green space. And we know that all of this equals to 5,400 meters squared. That's how much green space area we will have once that is paved. So we put that over in here. What we want to do now is create an equation in which we have this side equaling to 0, and normally we would be able to just go and make these equal to 0, find our zeros, find our what x equals to. We can't do it this time. We're going to need to take this side and make it into standard form to be able to deal with the 54 being on this side. So let's start with that. We're going to first FOIL our area. So what we end up getting is first times by each other, so 60 times by 100 gives us 6,000. Outside, 100 times by negative 2x gives us negative 200x. Inside, negative 2x times by 60 gives us negative 120x, and 2x times by 2x gives us positive 4x squared. What I'm going to do at this point is bring the negative 5,400 over and kind of rearrange it to something we're used to seeing in ax plus bx plus c format. So we have 4x squared minus 320x plus 6,000 minus 5,400. Go and collect all the rest of the like terms and this line. Plus what is left over, 600. Okay, looking at this guy, this doesn't look too easy to factor. And I don't really feel like factoring that either. So what we're going to do first, just to make our numbers a little bit easier using the quadratic formula, is I'm going to pull out this negative 4, this plus 4. So we're going to have 4 bracket x squared, 80 x, plus 6,000 minus 5,400. 4 bracket x squared minus 80 x, 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 80 plus 150. Okay, looking at this guy, yeah, this is definitely not factorable, at least not easily. So that means what we need to use is the quadratic formula. So let's label our information. We have A equaling to 1, B equals negative 80, and C equals 150. Let's put this into our quadratic formula. We get negative bracket negative 80 plus minus the square root of negative 80 squared minus 4 bracket 1 bracket 150 all over 2 times by 1. And you go and do that lovely equation. And we're going to get x1 is equal to 78.8, and our x2 is equal to 1.92. Okay, looking at this guy here, our x equaling 80.8. Now, is that going to work? If we had our x equaling to 78.8 and we took that away from 60, we're going to have a negative distance. That's not possible. We can't have that. So this one is a no-go. That is no use to us. Inadmissible. However, this guy right here, that's workable. That width will work in our situation. We won't take away any space. So then we can say, therefore, the width of the path is 1.92 meters. And I want to make sure it's rounded to the nearest 10th meter. Right now that's rounded to the nearest 100th. So we're just going to take away that too. Goodbye. And that's all the question's asking us. It's what is the allowable width of the path rounded to the nearest 10th meter? And here we have it, 1.9 meters. And that's the last of these problem solving questions. If you guys want to go, now do some of the homework. Again, if you have any trouble with it, put a star next to the questions you're having issues with, and we'll take it up the next day.